Hi viewers, welcome back to my class on mechanics of materials. In today's class, we will work out some of the questions asked for the previous gate exams. Let us start with the first problem. The rod PQ of length L with the flexural rigidity EI is hinged at both ends. What minimum force F it is expected to buckle? So PQ is the rod, it's hinged at both ends and it's subjected to a horizontal force F at Q. Since the force is F is horizontal and the component of the force acting along the axis of the rod is F cos 45. Since this angle if you extend the rod, this angle is going to be 45, that is just opposite angle. So if you extend the rod along its axis, the F will make an angle 45 degree with the axis of the rod, and if you resolve F along the axis, you will get F cos 45. The other component will be acting perpendicular to the axis, that will be F sin 45. So F cos 45, which is the component acting along the axis, is trying to compress the bar, and when F increases, the component which is compressing the bar will try to buckle this member. So this will act like a column when it is subjected to axial compressive load. So when the load increases, the member may buckle. So we need to find out what value of force F the member buckles. So buckling load for a pin-ended column is given by pi square EI by L square. Since it is hinged at both ends, effective length is equal to L itself. But the component of the force which buckles the rod is F cos 45. Cos 45 is 1 by root 2. So I substituted cos 45 as 1 by root 2. So you get F by root 2 is equal to pi square EI by L square. Or the force required to buckle the bar is root 2 pi square EI by L square. So much force is required to buckle this bar when it is applied horizontally at point Q. Let us work out another question. For a long slender column of uniform cross section, what is the ratio of critical buckling load for the case with both ends clamped to the case with both ends hinged? So you need to find out the ratio of the buckling load for the case with both ends clamped to the case with both ends hinged. Now both ends clamped means it is fixed end. So you know, for a fixed end the buckling load using Euler's formula, and both ends hinged, it is effective length is L. So buckling load generally it's given by Euler's formula, P is equal to pi square EI by L square. When both ends are clamped, effective length is L by 2. So you can substitute effective length as L by 2. So if the ends are clamped, you get a P. I used C subscript for clamped end or fixed end. Okay. So Euler's buckling load with a clamped end is pi square EI by L by 2 square. And if it's hinged end, effective length is equal to L. So for a hinged end, the buckling load is pi square EI by L square. Now this ratio you can take PC by PH, so that will give the ratio of the buckling loads. So if you take the ratio pi square EI by L by 2 square divided by pi square EI by L square, so now pi square EI will get cancelled. You get L square by L square by 4. This is L square by 4. So L square goes to the numerator, L square by L square by 4, or you get 4. So the ratio of the buckling load for a clamped end to the hinged end is going to be 4. So buckling load for a clamped end is going to be 4 times the buckling load corresponding to a hinged end. when the column lengths and other properties are same. So clamped end will take more buckling load, 4 times buckling load than a hinged end. Let us move to the next problem. Consider steel column hinged on both sides with a Young's modulus 200 gigapascal. Its height is 1 meter and cross section is 10 mm by 20 mm. What is the lowest Euler critical buckling load in Newton? So the column cross section is given, rectangular cross section 10 mm by 20 mm, and its height is 1 meter and both ends are hinged. So you know the Euler's buckling load P is equal to pi square EI by L square, and you can find out the moment of inertia of the column cross section. Since it is having cross section 10 mm by 20 mm, you need to find out the least moment of inertia. So there are two values for moment of inertia. One is bhq by 12 and other one is hpq by 12. So you can calculate 10 into 20 cube by 12 as one value, and another value is 20 into 10 cube by 12. So always you should take the cube of the least dimension for a rectangular cross section. So cube of least dimension is 20 into 10 cube by 12. So you have to use moment of inertia, least moment of inertia is 20 into 10 cube by 12. So that will give 1666.67 mm to the power of 4. You can also check the value 10 into 20 cube by 12, which will be much higher than this. So least moment of inertia is this value. So least moment of inertia you are getting, and effective length is length itself, and the length of the member is 1 meter or 1000 mm. So you substituting, you get pi square. E is Young's modulus 200 gigapascal is 200 into 10 raised to 3, and I value is substituted, and the length is 1000. So substituting that, you get 3289.87 Newton. So whichever choices given nearer to this value has to be selected. So if you write it in kilonewton, it's 3.29 kilonewton. Let us work out another problem. An initially stress-free, massless elastic beam of length L and circular cross-section with a diameter D, much less than L, is held fixed between two walls as shown. The beam material has Young's modulus E and coefficient of thermal expansion alpha. If the beam is slowly and uniformly heated, what temperature rise is required to cause the beam to buckle is proportional to dash. So we need to find out what temperature rise is required for this bar when it is fixed at both ends to buckle. So to cause buckling, what is the temperature rise? And the temperature rise will be proportional to either diameter or diameter square or diameter cube, etc. So you need to find out whether it's proportional to diameter square or proportional to diameter cube, etc. So the choices are given, you need to select the optimum choice. Now when the temperature rises, stress will be induced in the bar because the fixed ends will not allow that expansion. So bar will be trying to expand, that expansion will not be permitted by the fixed end. So when it tries to expand, the fixed end has to exert compressive forces on this bar. And as you know, the compressive stress induced is alpha delta TE. So you have studied that compressive stress induced in a bar when it is completely restricted from expansion is alpha delta TE, where alpha is the coefficient of thermal expansion and delta T is the temperature rise and E is the Young's modulus of the material. So you are given the length of the material, diameter Young's modulus and the coefficient of thermal expansion. These values are given. So then the stress induced is alpha delta T E. So once you know the compressive stress induced, you can find out the compressive force which is trying to compress the bar. So compressive force will be stress multiplied by area of cross section. So area of cross section you can find out as pi by 4 d square. Now this alpha delta T E is the stress multiplied by cross section area of the bar will give the compressive force, which is the force trying to buckle the bar. So when the temperature rises, since it is a slender bar, as already given that diameter is much less than L, so this will act like a slender column and it will buckle when the temperature rises. So what temperature rise is required for this member to buckle, that we need to find out. So Euler's buckling load is given by pi square EA by L square, and the force required to buckle is alpha delta T E A. Alpha delta T E is the stress multiplied by area. So this is the buckling load. So due to the temperature change, the compressive stress induced is the buckling load. So the load required to buckle, so when delta T increases, this will increase and it reaches the point where the member buckles. So you need to find out at what temperature change it buckles. So it's equal to pi square EA by L square. So you can solve for delta T. Delta T is equal to E cancels on either side. Delta T is equal to pi square I by A. So A is taken to the right hand side, I by A. So pi square into I by A divided by alpha L square. I by A, I is the least moment of inertia. So in this case, on circular cross section, there is only one value for moment of inertia. I by A is k square. K is root of I by A. I by A is k square, where k is the radius of gyration. So k is the radius of gyration, and we know for a circular cross section k is d by 4. Or you can find out I by A for a circular cross section. I is pi by 64 d to the power of 4, and the area is pi by 4 d square. So pi d square cancels, you get d square by 16. So that is k square, or k is d by 4. So you can directly substitute for k square as d square by 16, or k is d by 4. So when you substitute k as d by 4, you get d square by 16. Any solid circular cross section, radius of gyration is d by 4. So I by A is k square and k is d by 4. So you can substitute k square as d square by 16. So pi square d square by 16 alpha L square is the temperature rise required to buckle the bar. So temperature rise required to buckle is pi square d square by 16 alpha L square. Since the alpha is a material property and L is the fixed by the length of the bar, it is proportional to the square of the diameter. You can say it's directly proportional to the square of the diameter. You can say delta T, temperature rise required to buckle, is directly proportional to square of the diameter, or also inversely proportional to the square of the effective length. It is also inversely proportional to coefficient of thermal expansion. But these things are fixed. If length and alpha are fixed, it's only directly proportional to the square of the diameter. So delta T is proportional to the square of the diameter. Let us work out another example. A column has a rectangular cross section of 10 mm by 20 mm and a length of 1 meter. Find the slenderness ratio of the column. Now, assuming it is hinged end, effective length is 1 meter, effective length is L itself, 1 meter or 1000 mm. Least radius of gyration is root of I by A, and least value of moment of inertia is 20 into 10 cube by 12. As I mentioned earlier, 10 is the least dimension. For that value you can take the cube. So 20 into 10 cube by 12 divided by area is 10 into 20. For a rectangular cross section, 10 into 20. Cross section area is 10 into 20. So we'll get the value of radius of gyration as 2.887 mm. Now L by K you can calculate 1000 divided by 2.887 L divided by K. So we'll get the value as 346.38. So the choice is given nearer to this, you can select this value. Or if it is a fixed length, L by K is going to be half of this, because effective length is half of the length, and you will get L by K just half of this. Or if it's one end is fixed and other end is free, L by K is going to be double of this. Or otherwise, another case is one end fixed and other end hinged. In that case, the value of L by K will be this divided by, that is 346.38 divided by root 2. So you can check whether values are nearer to this. Okay, if this value option is not there, nearer to this option is not there, then you can check whether twice of this is there, or half of this is there, or divided by root 2 in that value. If that options are there, you can select it, because they are not mentioned the type of end condition. Let us work out another example. If the length of a column is doubled, the critical load becomes dash of the original value. So critical load of a column of length L is PE1 is pi square EI by L square. Now the length of the column is doubled, so effective length will become twice the earlier value. Okay, when length is doubled, effective length becomes twice of that previous value. So you will get the Euler's buckling load as pi square EI by 2L square. Now after doubling the length, the critical load is PE2, represented by subscript 2, and before this critical load is PE1. Now PE2 by PE1 will take, that is pi square EI by 2L square divided by pi square EI by L square, this value. So that will give 1 by 4. Okay, L square, pi square EI cancels, L square also cancels, so you get 1 by 4. So that is the value of PE2 by PE1. So that after doubling the length, so you get PE2 is equal to 1 by 4 of PE1. So that means after doubling the length, PE2 is the critical load after doubling the length, and PE1 is the critical load when the length was L. So after doubling the length, the buckling load is 1/4 of the initial value. After doubling the length, buckling load reduces to 1/4 of the initial value. So always increasing length will reduce the buckling load, because the column become more slender and the load required to buckle will reduce. The buckling load is inversely proportional to square of the length. When you double it, it will make 1/4, or if it is 3 times, if the length increases 3 times, it will become 1/9 of the initial value. So that way you can easily pick up the options. That's all for today. Thank you for watching.